If you remember, we started with the idea of sampling distribution. Apart from the uses of some of the sampling distributions of some statistics like summation xi or summation xi square or sum of numbers and sum of square of the numbers, there is one aspect of sampling which is not enough emphasized in many of the textbooks. Namely, most of the data, particularly economic data, or data which is to be used from the previously made surveys, censuses, and so on, these are not the data which are really collected with the same kinds of questions in mind which we wish to answer with that data. Consequently, if one have had an opportunity of collecting such kind of a data through a sample, what kind of a sample design one would like to have is a relevant question for those who do this data on fresh sample inquiry. But in most of the cases, this is not the situation. There is some data which has been collected for some purposes, and to the extent it is useful for us to answer some of the questions that we wish to investigate, we use that data. But in doing so, we cannot be really blind to the fact that it may not be coming from the kind of a sample design that we would wish to have if we were to answer it on the basis of a fresh sampling inquiry, if one have had an opportunity to design such sample and to collect the data. For example, there are certain concerns which are very relevant when you learn sampling theory from proper sampling theory books. Sampling is stratified sampling. Why do you need to make the strata and collect the data from different strata differently in different numbers, with different coverage, sometimes even with different questions? Because one is aware of the fact that the kind of population that we are dealing with is a fairly heterogeneous in attributes, in quality, in the nature of numbers that they are likely to throw up. In statistical parlance, the mean and the associated measure of dispersion such as variance in different layers of the universe that you are looking at may not be really identical. In fact, it is bound to be very, very diverse. And when you are taking the sample from such kind of a diverse data, which is classified, you call them strata or a group or sections, one has to ask the question, how much should I sample? How much should I sample from a particular strata? It has something to do with the differences in the mean that exist between strata. It has something to do with the degree of variability that exists between the strata. Depending on that variability and the closeness or the being farness of the means, one is going to choose the sample size from each of those sections or segments or strata in sampling language in a differential manner. And this is something which is probably not an address concern when you are going to look at the data which is typically called the secondary data. The secondary data is not necessarily collected with the same concerns which you would like to exercise if you have had an opportunity of collecting the kind of data that you want to answer. So you are supposed to look at the available data and address those issues, those concerns which you will typically raise prior to design the sample and the collection of data, even including the nature of questions that you ask in the questionnaire. They may not be directly addressable for you because the data are already there. So what one has to do is an exercise which is in fact a post-sample kind of an exercise. Just because the sample has already been collected, some data exists, that doesn't mean that you should not ask this question, you should not raise these concerns and try to address them. For example, it may be the case that the wages paid to the male workers and the female workers may be dramatically different. Are they really so? If they are so, in your sample, if you had an opportunity to design the sample, you will address this question and you will not necessarily pool the data. But now that the data has already been pooled, and if the data allows you to segregate them by gender, then you would like to in fact test, is the variability, the level of means are same across? If not, then probably pulling together the data of all laborers into one category and running some kind of a regression may be in fact not a very ideal procedure to do. And therefore, to address this concern, you are required to scan the data, you are required to re-examine or scrutinize the data. Statistical meaning of scrutinizing data is in fact to ask a question, are the data at hand are going to be comprising of different strata, different kinds of characteristics collected and merged together without addressing these typical concerns, so that a more representative picture of the universe that you are trying to portray and generalize about can be constructed or can be construed out of this data. This is something which has to be always borne in mind when you use secondary data, and in most of the cases economists are often required to use secondary data. At least for this purpose, one should ask the question, are different elements naturally formed into segregated different kinds of groups? Do they have means which are close enough? Do they have dispersions which are in fact different enough so as to treat them as beings belonging to different sections, segment, strata or so? Doing this is a question which you address during the sample design, but in the data which are already collected, you can't address it a priori, but at least in a posterior sense. And this is something which leads to what is often referred to as heteroscedastic variances. For example, the divergences in the consumption pattern of different income groups or different age groups may be very different, and therefore the variances may not be same. So heteroscedasticity, a problem raised in the textbooks that you often come across, it's something which is one major concern. Similarly, the way in which random element or the random stochastic factor which we add something when we write something like yi equal to a plus bxi plus ui. What kind of a ui is going to be? Is it going to be same? Is it going to be same across different elements, say households or different income groups? If not, then what? And when we say they are not same, statistically speaking, they are not same in two ways. A, their means are different, or their variances are different. There is something more. The random factors that affect, for example, even if you get people from the same income, is their spending out of that monthly income going to be same? No, it's going to vary. Some part of that variation is to do with the explanatory factor, but some of that is not. That is something which is a random component. Is this randomness that affects maybe ith household or ith strata, it's same as belonging to some other strata? This is something which is a relevant question that you should know. Similarly, does it happen that I observe it for say U1 and then I observe it for U2? Are U1 and U2 going to be related? Because when you run the regression, you put them together and there is a possibility that the relatedness between U1 and U2, and there are rather obvious connections that come from time series data, but it can also come from what is often called a cross-section data. For example, those households which are staying in the same vicinity may have probably a similar kind of a pattern. And that is something which can be called a spatial correlation between the random curves. In time series, in fact, it is obvious the price today is in some sense going to linger its effect on the next day and the same for the next day and so on. So that is something which is a relevant question, which is in fact called autocorrelation. The reason I am mentioning this is most of the econometric texts introduce the classical regression model by introducing certain terminology which is often called the assumptions of CX. Actually, the purpose of calling them to be assumptions is to show that there are certain properties of, for example, the estimators that we had derived, such as, for example, A equal to estimator like this, or B equal to summation xi yi minus n times x bar y bar, whole thing divided by summation xi square minus n times x bar square. This is our estimator. When is this estimator desired? In the sense of when does these estimators have desirable sampling properties? And in which sense can they be proved mathematically? That depends on, in fact, the nature and behavior of the random factors which is contained in Y. And therefore, modeling Y is not really merely exploring the relationship that Y has with respect to X. modeling wire also means the random component which is contained in that wire should also need to be scrutinized and examined such that this kind of a procedure of estimating, that is, when these kinds of estimators are to be used, in which conditions they possess desirable sampling properties, and as a consequence of those desirable sampling properties, they could be assuredly, securely used for the purposes of what we call statistical inferences about it, procedure that we are going to look a little later in the following lectures. But for the purposes of inference, for the purposes of judging the credibility of these estimated parameters with the help of such estimators, depends on the behavior of U. And that's the reason why textbooks start with a simplest kind of a case where this kind of a behavior is more assuredly available, in the sense that it is possible to establish certain kinds of sampling properties such as unbiasedness or being efficient, having the minimum variance compared to all other kinds of estimators, that is linear estimators. These claims are easy to demonstrate, are easy to establish when certain kind of a behavior of the random factor is present. Does it really mean that we believe that such kind of a random factors actually exist? No, it's other way around. In fact, we have every reason to believe that the random factors possess the characteristic than what we believe. But we need to understand when those properties that we start with, we would like to believe in deriving this, if violated, what statistical consequences does it have? Is to be examined, and therefore it is for understanding those violations, one needs to start with something which may not exist, which is unreal. And this is something which often happens in a number of logical reasoning. For example, to establish a claim that when something pushed in one direction, if not no force working on it, continue to move in a straight line. A statement made in physics improving Newton's law. Does anyone observe that straight line? No. But believing that argument that if there is no force, there is no reason why it would behave in any other way. And therefore, if it behaves in a certain manner, the nature of force which is forcing it to depart from that straight line can be explored better. It is for these purposes that we make this kind of assumption. It is not a blind faith that the error terms are actually behaving in the same way, which is often portrayed as the first condition, because it often leads to a misleading impression about statistical reasoning that people believe that regression model is useful only when these assumptions are fulfilled. No, in fact, one should be acutely aware that in most of the cases these assumptions are likely to be violated. And yet we would like to explore some such kind of a relationship, which kind of a caution that needs to be exercised, what kind of a correction to the data that needs to be made, if at all we are going to use this estimator. It's something which is highlighted when looking at the non-fulfillment of these properties which we presume. This is the reason why we start with assumptions. For example,